Good day, folks. This is tutorial number 6 in this playlist, which deals with kinematic simulation in the 3D Experiences platform. I want to remind you that what is buried in the 3D Experiences platform as a kinematic solver is actually the DMU kinematics workbench in the CATIA V5/V6 program. The problem that I'm going to be doing is a rotating arm. So there is an arm here which rotates about the base. So basically we have a revolute joint and at a constant angular speed. And from elementary math or physics, you can see the position of the tip of the arm as a function of time is given by these elementary sine and cosine expressions. And if you differentiate it, you get the velocity and the acceleration. Keep in mind because the speed is constant, the tip of the arm has a zero tangential velocity and a normal velocity, sorry, not a zero. What I meant was to say that it has a zero tangential acceleration, but it does have a normal acceleration, which is r omega squared. Now, this can be done, this is a simple problem, can be done many different ways, but I'm going to be using a direct formula, or what 3D Experiences call law excitation, and basically solve the problem. Okay, this particular problem is what is covered in chapter 3 of this book, which is about 8-9 years old. All right, so yep, very good. So let's go ahead and do this. We start with an assembly file. So we go to the assembly design. And let me actually make the arm first. So right click, insert 3D part. So this first one is the rotating arm basically. So on the horizontal, let's go to the part design. On the horizontal plane, I will sketch something that looks like that tip. The only restriction is that I have to put a dimension of 5 somewhere. We'll see that. This for a second. Shape of it doesn't really matter. The only thing that matters is the distance from here to the center should be 5. Okay, so let me see now, dimension from this point to that center. I want this thing to be 5 inches. That's all. Okay, good. So exit. And I'm going to pad this thing by maybe 0.3, so it looks, 0.3, so it looks nicer. Okay, good. We go all the way to the top and insert, right click, insert. That's going to be the base. Insert the 3D part. This is going to be the base, so double click on it on any convenient plane, on that horizontal plane. I will draw a circle. Let me actually draw it right there. This is going to be the base, and exit, pad it in the other direction. Yeah, that's good. All right, good. Now we're going to create our constraints basically, or create our joint. So we go all the way to the top in the assembly design. Let me first fix the bottom. So we can go here, say fix the space, that's fixed. And now we're going to create a revolute joint between this and the base, that arm and the base. So here is a revolute. Okay, the different ways of doing it, the templates allows you to decide on which one you want to do. For example, I can do axis and axis, and then two planes which are tangent to each other or in contact with each other, etc., etc. Or I can do it with coincidence, two planes being coincidence. Let me go ahead and do. Doesn't really matter. I'll do this one. Okay. So we need axis and axis. So this axis and that axis, and plane, coincidence plane between this plane and the bottom plane of this. Okay. Now, to control the motion, I'm going to have to create a command between two planes. So I'm going to use the angle between, for example, this plane and that plane. Okay. And notice that if you move this thing, this will turn as it's supposed to. You can see that. So let me make it, for example, 30 degrees. You can see this. Yeah, but I'll put it back to 0. So put it back to 0. Good. I don't want to check contact. Okay, good. Now we go all the way to the top, and we go to mechanical systems design. Let's create our mechanism. I don't have to check these because they're already checked. Good. So a mechanism has been created. There is a revolute joint and there is a fixed point, or fixed part. That's what I meant. That's pretty much it. You can always check it. If you click on this mechanism player, you can check to see whether it's going the way you want it, reset. In the event that you want to change the orientation of this motion, it's also possible. So we're going to be see that there is an arrow here. Let me see if we can do that here. Right click. We can do it from here, but later on, see, this will not allow you to change the direction. But we can do that later. Okay, good. So that takes care of here. So let's go ahead to mechanical systems experience. And all right, so let's go ahead and create a law excitation. So the support is that command that we created right there. And since I'm going to be inputting the formula, so I just click on this, see that? Click on that. And then I go and input whatever I want. So angle equal to omega t, right? So the different ways of writing it. For example, you can say 360 DEG underscore S. Remember, 360 degrees per second times time. That's one way of doing it. And notice that the left side is degrees, the right hand side is degrees, no problem. Or I could have done here turn per minute, 60. I could have done 60 turn per minute. So for example, I can go, let's see if we can change this thing here. 60 turn per minute. Go. Yeah, same thing. Didn't complain, etc. So basically, that's what this thing was saying. 60 RPM, turn per minute. Can't type RPM. Say OK, no problem. And then we say OK. Good. So now we create a, well, let's create a probe here too. For example, the tip of this, create a position, speed, and acceleration sensor or probe, as 3D Experience calls it, but CATIA calls it speed acceleration sensor basically. So we say OK. All right. Now we go create a scenario. This is the excitation that we created. We use it. How many turns? Let's make it over 2 seconds. Okay, 2 seconds means this is going to go twice, around twice. So we do it over 2 seconds, and obviously we have to make this thing substantially smaller so that we get the different frames. So we say OK. Now, can I flip this direction? No, see, it won't let me flip the direction. So if you want to flip the direction here, what I need to do is put a minus sign in front of that formula. Ordinarily, I should be able to take this thing and, flip it, but I don't see it here. It doesn't let me do that, but that's okay. So let's go ahead here. Let's go to compute and generate results. It's going to go twice. Say okay. Good. So can we check the plot? First of all, you can animate this thing the way you want it. Let's play it once, twice, and then with this you can control whether you want it to go continuously or in one direction, etc. This is going to go forward, whatever. This one is going to go forward and backward. Okay, so let me stop this. Okay, so click on the view scenario results. Now, one thing I forgot to do, I did create a probe. Okay, yeah. So under specification, I should be able to get other things that we can plot. Right now, if we plot this thing, it's going to be a linear rise in the in the angle. You can see that. But let me see now. I'm not sure why the probe did not work. Let's go double click on this thing. Okay, one support is 1 point. Okay, that's fine. Uh, that's fine. Let me see if actually probe was included in my scenario. Let me cancel that. There's my scenario. Probe. Oh, but it was not included. Okay, so I created it but was not included. So let's go ahead and run it again. Good. Now click on the results. There's all kind of things that we can plot. I don't want everything, so deselect all. Let me plot the angular acceleration, the magnitude of the angular acceleration. Remember, tangential acceleration is 0, uh, and the normal acceleration of that point is r omega squared. So let me say, if I do linear, yeah, where is that thing? Angular velocity, angular acceleration, right there. Okay, let's check this thing and plot it. Okay, so angular acceleration. This is all 0. That doesn't make sense. Not angular acceleration. Linear acceleration is what I want. Okay, linear acceleration. Plot. Constant. R omega squared. Now, what is R omega squared? R omega squared is omega is 2 pi radians per second. So if you take 2 pi, square it, you get 4 pi squared, and multiply it by r, so 5 times 4 pi squared. So that's 20 pi squared. Pi squared is approximately 10. 20 times 10 is approximately 200. And the plot is, yeah, right there. So this is your r omega squared value. Okay? And that's pretty much it. Oh, let me plot something else. Let me plot the position, x and y position. So for example, of that point, let's see now, x vertex and y vertex, we should be getting a cosine and sine curves. So, okay, so you can see that. Because that's what this is saying, x equal to this, okay? and you can plot the components of velocity also. That's pretty much it. Good luck.